So we left off with this question. If you fire a bullet and you drop a bullet from the same height at the same time as you fire it, which bullet hits the ground first? Well, the bullet is a projectile, and this is also a projectile. It's given no initial velocity at all, but it's subject only to gravity. Both of them are subject only to gravity. Acceleration due to gravity is downwards, and that is the only only acceleration present. And so if they're equal mass and everything's equal between the two bullets, right? That was the assumption. They will both hit the ground at the same time. X and Y motion are independent from each other. Just because this one's traveling a distance in what we would probably consider the X direction here, and this would probably be the Y direction, right? If we were to start analyzing this problem. Just because this one's moving in the X, it does not affect how it is falling in the Y. They're completely separately handled. There's zero acceleration in the X. We're ignoring air resistance, right? So they both hit the ground at the same time. That's kind of wild the first time you come across that, but it's true. It's true. So convince yourself of this fact. You will be that much further ahead along your way to understanding projectiles, and more importantly, acceleration and motion in X and Y dimensions. So we're going to do some examples here, and just like I did last time, we're going to go over some projectile motion problem solving strategy first. And these are my notes, and instead of rewriting things, we're just going to write it, show it right up here. Hopefully this is big enough for you to see just fine. I think it is. Okay, so projectile motion problem solving. So when you come across a projectile motion problem, which you will in the homework, but you might in the future as well, it's important to remember that acceleration is always downwards, right? And it has a magnitude g, and g is specifically 9.8 meters per second squared. Or 9.80 if your homework or textbook specifies that it wants it to have 3 sig figs. The equations that we derived, all of the motion that we're talking about, applies only once the projectile is in flight, not while it's being shot or thrown. So while I'm throwing it, I'm giving it some force, which we'll talk about in the next lecture, and force has acceleration associated with it. And so when I'm throwing it, or when it's being shot in the cannon, there's other accelerations in the X that are present, but it's only a projectile once it is released. It's released from the cannon or whatever is shooting it. And now you just have the object traveling along its path. Free fall, being only subjected to acceleration due to gravity. So to set up the problem, I've identified 3 steps here. Step 1 is identify your coordinate system. It's largely going to be the same, but there's some problems that are weird, and we're going to look at one actually. So define your coordinate system, and this determines everything else, right? So usually you want y to be your vertical axes and your x to be your horizontal axes, and you want the origin to be where the projectile becomes a projectile, where it begins its flight, right? And so if you do that, if this is possible to do for the problem, then you have a few things right off the bat. The acceleration of the x is 0, and that's throughout the problem. The acceleration of y is minus g, right? It's in the downwards y direction, and so it's minus, it's negative. And the starting position, x naught and y naught, are 0. And so your r position vector, 0, 0, right? That's how we would expand that. We'll put x and y together. And then hopefully you're given some other information that allows you to solve for the rest. So as you read the problem, step 2, lists the unknown and known quantities. So you might not be asked to solve for every single unknown, right? You might not be asked to solve for a scenario in full. So you don't have to list unknown quantities, just the ones that you're asked to solve for. But as you read the problem, make sure and identify the quantities that it's telling you. And then make your diagram, given your coordinate system that you've identified. And on your diagram, right on your diagram, start filling in the known quantities. And you can represent the ones that you don't know with symbolic quantities. So you might not know what it is, right? But if it's shot at some v naught and some angle, maybe v naught is equal to 2.6 meters per second. And the angle is perhaps unknown. Then you just leave it as alpha naught, right? If they don't give you the angle. But they would have to give you something else. They might give you Vx naught and Vy naught, and then you can find the angle and whatnot. Okay. So in order to pull those quantities out of the problem, you want to be alert, just like before, for the implicit keywords that exist in a problem. So be alert for implicit keywords in the problem, and translate those to symbols. So if it says when blah, 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 well, that refers to what value of t is it when this blah, blah, blah happens. What height means what value of y, because y is the vertical, if that's how you defined it. Where is it when velocity is blank means what are the values of x and y when v equals this. And there's this when here, and so specifically you have v at some certain time that you're going to plug in. So when v is equal to blank, when v at some time value is equal to blank, what are the values of x and y, right? So you're translating words to symbols. This is definitely something that you do in a lot of math classes, but here's our new language that we're talking in. Oops, I just messed up all my underlinings. Okay, and then don't break the trajectory up into segments. It's really tempting if it's talking about, on the upwards part of the journey, and then later it's talking about, downwards here, or something like that. It's tempting to think, okay, so for here I'm going to have this, and then for this over here I'm going to draw a completely different diagram and analyze it all separately. No, draw just one diagram. The particle takes one path, right? There's one flight. And it's just asking you about various parts of that path. And so use the same axis and just and use the same time scale throughout the problem. So have t0 equal when it was shot. Never have t0 equal some later part of the trajectory. Have it be when it's right when it becomes a projectile. And then, as always, evaluate your answer for reasonability, and this includes units and magnitude. All right, and hopefully you jotted down the equations that I boxed in last time. I don't have them written on this sheet, so I won't be completely bringing them back for us to stare at and pick out the right equation. But they're a little bit less confused or involved than the last one. The last set of equations anyhow, because we have x, y, vx, vy, right? All right, so our first example is this one. It's a baseball and bat. It's nice and big. Trying to see what you can see. Okay. So a batter hits a baseball so that it leaves the bat at speed. Speed has to do with velocity, but it's only the magnitude of velocity. not the direction, but rest assured we will be given the direction as well, so that we can figure out the rest of this problem. At speed, v naught equals, see, they're nice to you. They're nice to you and they give you v naught equals, but if it didn't tell you v naught, you would know that when it leaves the bat, that's the moment it becomes a projectile. And so that's talking about time equals 0. And speed is the magnitude of velocity. So v naught is equal to 37.0 meters per second. At an angle, and if it wasn't nice to us, we would still be able to know that this is the initial angle, right? Because it's the angle that it leaves the bat at. So at time equals 0, the angle is 53.1 degrees. All right, so that's the initial information. That's all we have. But you know what? That's all we need too. So find the position of the ball and its velocity. So magnitude and direction at time equals 2 seconds. So A here, I'll pick a color. A is saying time is 2 seconds. That's the moment we're analyzing. 2.00 seconds. All right, and find the time. Find the position of the ball and its velocity. So we have equations to use, but first let's draw a diagram. So we have a projectile. It's going to look largely like what we've drawn in the past. This is going to be x, and this is y, and we have the path here. Path is going to be something like this. It's a nice hit of a baseball, yeah? So this is the bat, the batter maybe, right? So this is the bat. And he just swung, and the baseball, I don't know, I can draw a baseball very specifically. There's a baseball, and it's going and going, right? So what we're given is the initial velocity. Velocity I think I did in like red. Velocity is something, and I'm going to make it larger. Just so we have some clarity here. That's velocity. And that's the initial velocity, so v naught. And we are also given the angle from the horizontal. That's alpha naught. So v naught we're given is magnitude anyways. Okay? So the magnitude of v naught is 37.0 meters per second, and the angle is 53.1 degrees. All right, and so now our baseball's here. It's 2 seconds later. So I'm going to say at this point here, t equals 2 seconds. Yeah. Neither of our axes are time, right? It's important to point that out. This is x, which is a position, a spatial dimension, and y is vertical spatial dimension. But you're time stepping as you're moving through its path, right? So this position here, we're just kind of calling it t equals 2 seconds. It may be over here. I don't know, but we will definitely find out, because if we find the angle to be 0 degrees at wherever it is, then we know it's at the top. Or if we find the angle to be negative, then it's over here falling, right? Negative with the horizontal. That would be a negative angle. So we can figure it out. But I'm just kind of labeling in our diagram somewhere, saying, let's suppose this is 2 seconds. Maybe it's accurate, maybe it's not on our diagram. But the numbers we come up with will be accurate. All right, so what we want, coming back here, what we want, so at t equals 0 seconds, we want to know what x is. So x is something, y is something, and we also want to know its velocity. Velocity is something, the magnitude of velocity when it's at this time, and the angle that it's at from the horizontal is something. So we have a lot of unknowns, and we're only given time and the initial velocity and angle. Can we find all of this stuff? Well, we have equations for x, y, and we have equations for vx and vy. Those are the 4 equations that we worked with before, right? And so we want to use, to start just from the left and work our way right, we want to use this equation. X is equal to v naught x times t, right? Remember that v naught x is simply v naught x is simply this part here, right? Which is v naught cosine of this initial angle. And so in our other equation we had it written fully out, v naught cosine alpha naught. So we can write this if we want. V naught cosine alpha naught times t. Right? That's what we want to use. And the other one that we want to use, I'll do it below, is y is equal to v naught y times t plus 1/2 gt squared. We want to use this, but we need these quantities first. And so, just like I expanded it, we can expand it, right? So v naught sine alpha naught times t plus that 1/2 gt squared. So these are the equations that will get us there. This is a very sloppy t next to plus sign. Alternatively, we could just find out what v naught x is, because v naught x is equal to v naught cosine alpha naught, right? This quantity, that quantity. We could find out what v naught x is and then plug it into there, but it's the same difference, right? It's the same difference. So we have written it out. So this means that x is equal to, right, this part here, x is equal to v naught. Our v naught was 37.0 meters per second. Times cosine of the angle 53.1 degrees. We can do this if we wanted to be really pedantic. Times the time, 2.00 seconds. Is this going to get us position? Cosine of some degrees, that's going to get us just a number, a unitless number. Seconds in the numerator, seconds in the denominator, they're going to cancel. We'll be left with just meters. So yeah, it's going to get us a distance, right? Position units. So if you plug that into your calculator, then for x, you should get 44 0.4 meters. And then similarly for y. Y is equal to 37.0 meters per second. Right, I'm taking now this whole equation, and plugging it in for y here, right? Times sine of 53.1 degrees times 2 seconds. And we have a little extra bit for y though. Plus 1/2 9.8. We'll use 9.80 so we don't cut off our sig figs because the rest have 3 sig figs. Meters per second squared times 2.00 seconds squared. Is this going to get us distance? Is this going to get us meters? Well, we have, right, 2 seconds in the numerator, and seconds squared in the denominator there. And here we have seconds in the numerator, seconds in the denominator, same as before, so yes, it does. And so this works out to, slide it over. If you plug that into your calculator, and make sure that your calculator is in degrees if you're plugging in degrees, or radians if you're plugging in radians. Right? Double check that, especially before doing a bunch of work. Right? So if you plug that in, you should get 39.6 meters. That's y. Alright, so next, our task was to find v, and the angle that it made with the horizontal. Right? So already what we've solved for, this x and y, we could find, like I had said in the previous video, we can find the position vector, and we can find how much in the x and how much in the y it is, because we have r, the position vector, is equal to x, y, right? And we have x and y now, so we can find out exactly where it is, right? But we don't quite know what its velocity is, and we don't know what the direction of the velocity is. So we don't know if it's heading up or down yet, but we know where it is. So now, to find velocity, what we want to use for velocity, go back to the same one because we're still on part A. What we want to find is magnitude of velocity is Vx squared plus Vy squared. Right? That's what we want, but we don't have Vx and Vy. Right? All we have is xy and the time that we're talking about. The other thing that we want to use to find the position or the direction of the velocity is the angle is equal to the inverse tangent of Vy over Vx. Same thing, we need this Vy and Vx. So how do we find Vy and Vx? Vx is simple. Vx is simple because it's not changing. There's no acceleration in the x direction, and so Vx is equal to V naught x. This means the initial velocity component in the x direction is equal to the x component of the velocity at every future time until it stops being a projectile. So we have Vx because that is our V naught x, or V naught cosine, so here, V naught cosine alpha naught. That is V naught x. But V naught y is different. Vy is different. Vy is equal to V naught y minus gt, right? So it's whatever the initial velocity in the y was minus whatever the influence of the acceleration due to gravity is at the time that you're talking about. This whole element of our equation accounts for the acceleration due to gravity that is being subtracted from the y velocity, right? So the further you go in time, the less positive y velocity there will be. This would be one time, this would be another time, be another time. Eventually there's none because it's reached the top, and then it starts going down again, right? So eventually it hits the ground. That's the progress here. So this is our equation. We simply plug in. So v naught y is v naught sine alpha naught. Then we have this minus gt. And so v naught is 37.0 meters per second sine 53.1 degrees minus 9.8 meters per second squared times 2.00 seconds. And if you compute that out, making sure your calculator is in degrees, then you should get 24 point, no. You should get, where am I? 10 meters per second. And Vx, I didn't write out the numbers, so Vx is that same thing here, 37.0 meters per second times cosine of 53.1 degrees. Yeah. Which is 22.2. 22.2. All right. So now we have Vx and Vy. That's what we needed before. So now we can use this equation here. And we can also use this equation here. And we're very close to being done. So the magnitude of the velocity is Vx squared, which is 22.2 meters per second, plus Vy squared, 10.0 meters per second squared. Compute that out, and now you get this 24.4 meters per second. So that's how fast it's going at that point. We still would not know whether it's traveling up or down. We just know how fast it's going and its exact position. But we don't know what angle it's making with the horizontal until we find out this last piece, alpha. The angle it's making with the horizontal is the inverse tangent of Vy over Vx. So Vy is 10.0 meters per second. Vx is 22.2 meters per second. If you compute that out, you get 24.2 degrees, and that's positive. So it's still on its way up. So my guess up above was correct. It's still on its way up. And that might represent about where it is. Maybe it's earlier, maybe it's here, I'm not sure. We could label our axes and figure it out exactly, but we have the math of it. If the angle were negative, like I said, it would be over here on its way down. All right, next example. Get all new space here. All right. Oh, wait. Not next example quite yet. There's more to that first example. So let's see, I'll just bring it out again here. Part B we'll do all new. Alright, so part B says find the time when the ball reaches the highest point of its flight and its height h at this time. So find the time the ball reaches the highest point and the height h at this time. Well, what does it mean when the ball is at its highest point? So first of all, keywords, when, right? Find the time, t, when. I don't think I can reach up that high. When, let's go with a new color since we're on part B now. So find the time t, so t equals something. That's one thing we're trying to find. When the ball reaches its highest point, right? So when the ball reaches its highest point, what is happening? Well, the angle is going to be 0. That's something. So the angle at time t that we are concerned with is going to be 0 degrees. So we can go with that. Another thing that must be true is the vertical velocity, Vy, at time that we are concerned with. Or maybe I'll write it this way. Vy at time equals what we're trying to find out. That must be 0. It's not traveling up or down, right? When it's at the top here, for that moment it's at its peak, it's not going up or down. Remember, the full velocity vector was the x component, right? So that means that at this point, Vy is equal to 0. So we have a couple things we can go off of. You can choose and do your own work and go off of one and check back and see if you get the same answer. I'm going to go off of this piece here. Vy must equal 0 because it seems like it'd be a little bit easier. So we have this equation for Vy. Vy is equal to V naught y minus gt. We worked with this in part A. And we know that Vy must equal 0. So this whole thing must equal 0. So now we just solve for the time, right? Because that's one of the first things that we're asked to look for. Find the time when. Well, here we have our equation. G is a number. V naught y we know. So find the time. Well, time is going to be equal to V naught y over G. And if you plug in the numbers, you get that time to be 3.02 seconds. So this event, the peak of its trajectory, occurs at 3.02 seconds after it is launched, after it's the baseball's hit, rather. Okay, and now find the height. And its height h at this time. So height is just the vertical distance from the ground, right? So if this is y, right, this is the ground, then the height is just the value of y. And so find the value of y at this time. So value of y at the time t equals what we just found, 3.02 seconds is equal to what? Right, and now we know this is that, but that no longer serves us to do anything anymore. So y, when time is 3.02 seconds. So the equation for y, go down a little bit. Equation for y is v naught y times t minus 1/2 gt squared. So we have a bunch of times to plug in. We got that. We have g because that's just 9.80. And v naught y we solved for that in the first one. So it looks like we got this made. So if you plug everything in, you should get 44.7 meters. So at the top of the trajectory, at its peak, right, this height from here to the ground, this distance we just found is 44.7 meters. And the time at this point is 3.02 seconds. So we're starting to fill out the whole picture here. And all we were given, remember, was two pieces of information. The magnitude of velocity that it was hit at, and the angle with the horizontal. It's kind of remarkable. So now, what does it want next? So that was B. If I'm not mistaken, we're done with B. Yeah. So now C. Let's see. Let's go purple. C. Find the horizontal range, and they help define what that is. Horizontal range R, that is, the horizontal distance from the starting point to where the ball hits the ground. So the horizontal range R. So C is going to be purple. Right? And if we go all the way back to our picture, hey, we weren't that far off, I wouldn't say, because 3 seconds we found is right at the top here. This is t equals 3.02 seconds. And this was 2 seconds, so maybe it's a little farther back, but we weren't too far off in our guess. Horizontal range, it tells us, is this distance. Horizontal range, that is the horizontal distance from the starting point, that's the origin here, to where the ball hits the ground. Well, what does that translate to in our symbols? Isn't that just the value of x, right? The value of x at this point here. So if we can find x, let's go all the way back down to our new space. All right. So we're on C now. C. So we want the value of x at some condition. When the ball hits the ground is the condition. But what does it mean when the balls hit the ground? What must be true? Well, there's a couple things that must be true. For one, here, let's think smarter here. For one, what must be true is this angle with the horizontal at the point that it hits, right? Trajectory for this. That angle is the negative of the initial angle. So whatever angle is shot at, if all that's happening is gravity, then the final angle, that's negative 53.1. That's when it completes its trajectory, if the ground is nice and level. So we can go with that. I think angle conditions are a little bit more difficult than anything else. So what else must be true? Well, when the ball hits the ground, what's the value of y? What's the y position? What's the height? The height is 0. So this here is y equals 0, right? That condition is y equals 0. I think that's easier to go off of. Maybe there's other things that you can think of too that we could have gone off of. But let's just go off of that. So, what's the x direction when y is equal to 0? That's kind of weird. Let's expand that. What's the x value when t is equal to, so the time is equal to when y is equal to 0. So whenever this event happens, y is equal to 0. Whatever time that corresponds to, that's the x that we're trying to find. So let's deal with this first. So when does this happen? Right? So when is y equal to 0? Well, that means we're solving for t and setting y equal to 0 in our y equation. So v naught y t minus 1/2 g t squared. And y is equal to 0. That's the event. Y is equal to 0. And now we solve for t. So t, this is a quadratic equation. So t times the quantity v naught y minus 1/2 g t is equal to 0. So there's 2 times that t is equal to 0, right? Or 2 times that y is 0, rather. There's 2 t's that correspond to when y is 0. T equals 0, that would be this t. And also, t is equal to 2 v naught y over g. So this is not false. It's not false. We asked math the question, and it answered, and it gave us something beyond what we expected. But it's true. We said, when is it true that the baseball is on the ground, or at the origin, right? Or at y equals 0, at 0 height? Well, the way that we defined our coordinate system, right when we hit it, that's y equals 0. And also when it lands over here, that's y equals 0, right? I guess we're ignoring the height of the person that's swinging the bat, right? So it's not really hitting the ground, but we're going to go with this. And so it gave us, well, y equals 0 when t equals 0, which is true. But we can ignore that, because that's not what we were looking for. We were looking for this one here, y equals 0 when t equals 2 v naught y over g. 2 v naught y over g. Does that sound familiar at all? We can compute that. I mean, we have that. We know v naught y and we know g. And we know the number 2. But look, over here, v naught y over g was 3.02 seconds. So this is just twice that. Twice the time that it was at the top. So this is 2 times the highest point. T at, I'll say peak. Which is an interesting thing of trajectories. So in a trajectory path, this point is half of this point, right? Because you don't have any acceleration in the x direction. And so whatever time it took to travel in the x direction this far, it's going to take twice that to go the rest of the way. So this is the midpoint. It's not going in the x direction any faster here than it is there. Just like when you fire the gun, the bullet, that question we were thinking about. Right after you fire the gun, the bullet has no more x component velocity right after you fire it than it does when it lands, if you ignore air resistance. So anyway, we already computed this. So this is just twice 3.02. So that's 6.04 seconds. Well, it's not our answer. It's one thing that we need to get to our answer. So what was this question asking again? The horizontal range. Find the horizontal range when the ball hits the ground. When y equals 0. So now we have t, 6.04 seconds. And now we just need to plug in for x, right? So we've gotten this t, when y equals 0. So now x is equal to, so now we're trying to find x at time equals 6.04 seconds, right? So x is equal to v naught x t. And so if you plug that in, you get 13.4 meters. No, 134. 134 meters. And that would be twice the horizontal range of when it was at its highest point, right? Because you're just plugging in 6.04, which is twice 3.02. So if you did the same calculation, but we plugged in 3.02, and that was the time that it was at its peak, you would get 134 divided by 2 meters. All right. So we'll leave that floating in the sky, and we'll grab our next equation, or our next example. I believe that was the last thing we had to solve for. Yeah, okay, so we're done with that one. Finally, you say. Finally. This one I chose because it's a little bit odd. It changes things just a little bit from what my strategy suggested for you. Well, maybe not exactly, but it's a little different. Go ahead and read this. You throw a ball from your window 8 meters above the ground. When the ball leaves your hand, it is moving at 10 meters per second at an angle of 20 degrees below the horizontal. How far horizontally from your window will the ball hit the ground? Ignore air resistance. So I want you to try something out here. I want you to do your best on your own. So hopefully you can read this just fine. I'll try to make it nice and readable. Pause the video and draw your own diagram. Take as much time as you need, draw your own diagram. And then I'll go through it and you can compare and see what threw you off or that you are on track. Okay. So you have your diagram that you did. Let's go through it ourselves here. Let's go through it together. That's not it. There. Okay. Because this is a weird one, right? You're throwing something out a window. You're not. It's not starting on the ground, or if it is starting on the ground, it's going downwards, right? It's falling out of the window. So what we're wanting to do, what we're asked to do, is find x, how far horizontally from the window, so x, will the ball hit the ground. So that condition, the ball hitting the ground, is when t is equal to something, right? And that something is dependent on y being something, right? So when the ball hits the ground, well, if the window is 8 meters above the ground must be equal to, so new color. So ground equals y is negative 8.0 meters. Right? And so what we're wanting to do is find, so we want to find when, so when does that happen? So find when the time, right? When is y negative 8.0? And then after that, we're going to use our when to find x. That's the game plan. All right, so let's draw a diagram. All right, so here's our ground. Got to start with the ground, right? Here's ground. Comfortable place to start. And since it's the ground, we're going to give it little tick marks. Tells us that is ground. Not electrical ground, but ground. All right, and we have a window. And this is going to be the x horizontal direction, but I'm not going to make that our actual axes. We have a window that's 8 meters off the ground, right? So let's say our window is right there. And I'm going to make this, the height of the window, our x horizontal. And if you didn't do it this way, you're not wrong. I just think this is a nice way to do it. That's our positive x direction. And this is still going to be positive y direction. Oops. You could, of course, make down positive y direction, and you'd have to make sure that your gravity is not negative 9.8, it's positive 9.8. Many ways to do the same thing, but this, I believe, is the easiest way to do this. And so this, I'm going to make my origin right there. This right here is 0, 0, xy. And so that means that this is y equals negative 8.0 meters. Okay? So this is our window. You throw a ball out the window, all right? And when it leaves your hand, it's moving at 10 meters per second at an angle, so it's going to have some trajectory. The trajectory is probably going to look, let's see, what did we go with? Oh yeah, we were green for position. So its trajectory is going to, so angle of 20 degrees below horizontal. So maybe it's helpful to start with its initial velocity, huh? So maybe that's 20 degrees. This would be 45. This might be 30, and a little less is 20 degrees. Something like that. So this is our angle, our initial angle, and that's 20 degrees. And it's below the horizontal, so to negative 20, right? Negative 20. And the velocity vector, this is our velocity vector. And that's equal to, the magnitude of such is equal to 10 meters per second. All right. And so if that's the case, if we were drawing the trajectory, something like that, right? It's falling down to the ground. It's going to reach the ground at some point. All right. So what we want to know is at the point that it hits the ground, how far horizontally from the window did it travel? So we want to know, well, we want to know what this value of x is. X equals something unknown. That's what we want to know. That's the value of x that we're searching for. But first we have to find when. Find when. Find when. When. Then find x at that t. So how do we find when? So first, what is the condition when this event occurs, right? When this occurs, what is true? What is true when this occurs? We can't really talk about angle anymore because it didn't start from here, so we can't mirror where it started with the inverse of the angle like we talked about before. But one thing that we can always go back to is position. We know its position here. So when it is here, it is at y equals negative 8.0 meters. That's its position. And so t at y equals something. Before it was when y equals 0, but now we have y equals negative 8. But it's the same procedure. So y equals v naught y t. Oops, that would be vy. Y equals v naught, no, that was right, v naught yt minus 1/2 gt squared, right? V naught y minus 1/2 gt squared. And the y is equal to this y, negative 8.0 meters. And this v naught y here, right? That's v naught sine, because we're talking about y, alpha naught, times t, minus 1/2 gt squared. And that is equal to negative 8.0 meters still. That's our equation. And so we're solving for t. We're solving for t. So if you plug, if you plug in the numbers and you solve for t, right? So you factor out a t, and you get v naught sine alpha naught minus 1/2 gt. Oh no, this one we have not 0 over here, so we can't factor and solve. We have to use the quadratic equation. You have to set this up like a quadratic. So we have minus 1/2 gt squared plus v naught sine alpha naught t plus 8.0 meters. Symbolically, it would be y, But we don't want to lose track of that 8. But anyway, if you plug in your numbers into the quadratic equation, this being, your A, and this being your B, remember that? This being your C, because this is now equal to 0. You get 2 answers for t, right? Because it's something plus or minus. Remember, something plus or minus something. That's how your quadratic equation stuff is going to come out. So one of the values for t is negative 1.7 seconds. What does that correspond to? Negative 1.7 seconds. So that's before it left the window. Well, when you're computing this, mathematically it's talking about this whole arc, right? Just like before we got 2 values. But this one doesn't actually even exist because the path would have started way over here, right? Y would equal 0 if you kept going this way. But we know that our problem doesn't go like that. Our problem starts here. And so this other value for y equals 0, which would be somewhere over here, it's a phantom value. This is t equals negative 1.7, I believe it was. Yeah, seconds, right? Not an x value, not a y value. This is a time. So there's some event. That's a phantom value. And you have to think about what it refers to and whether it is relevant or whether it even exists. In this case, it doesn't even exist. It's a phantom value that does not exist. So it comes out of the equation because it comes out of that mathematical function, but it doesn't exist in real life. The other one is t is equal to 0.98. 0.98 seconds. And that is the time that we want. It's the only time, unless you're talking about the ball bouncing. That is this time here. It leaves the window, it comes down, and it hits the ground. Y is equal to negative 8 meters at this time. This is when it hits the ground. So now, remember our game plan was to find when, and then use the when to find the x at that time. So now all we have to do is plug in that time to the x. So now we can find x at time equals 0.98 seconds. To be explicit, right? You could just write x equals and know what time we're plugging in. V naught x t, which is equal to V naught cosine alpha naught times t. And if you plug all of that in, you get 9.2 meters. 9.2 meters. That's the value for x when the ball hits the ground. So that's the horizontal distance covered when the ball hits the ground. That's this distance here. What was it? 9.2. There it is. So a little bit of a weird one. So I chose to show you this example. Other weird ones might come up, and so you might have to get a little bit creative. But that's how it goes. All right. Next video, we'll talk about uniform circular motion.